Hello everyone, we hope you all are doing well. Welcome to the webinar by National Space Society, USA, Mumbai chapter. NSS is an educational and non-profit organization dedicated to the creation of spacefaring civilization. Here, we aim to spread awareness regarding space and STEM amongst space enthusiasts and students, providing them with a platform to interact with experts.
Today's session, we are pleased to have Dr. Garima Singh, an expert in developing technology for imaging of exoplanets with an experience of over 4 years as postdoctoral fellow at prestigious research institutes like Observatoire de Paris, that is Observatory of Paris, and JPL, Jet Propulsion Laboratory. She is joining Hertzberg Astronomy and Astrophysics Center in Victoria, Canada, as a postdoctorate fellow. We are immensely grateful to have her and really appreciate her efforts for this webinar. She is here to introduce the technologies used in capturing the images of exoplanets. Garima ma'am, over to you.
Well, thank you for the introduction. And even though we can't see each other, hopefully this talk will be engaging and not boring. And first of all, I hope that all of you have had your dinner so that you're not hungry while I'm talking. Okay, so I don't know your background, guys. So I hope the talk will be still understandable. And perhaps if you're not in the field of astronomy, you might find it interesting because I really try to make this talk as understandable and as clear as possible. But I think the idea is also to not only to introduce you to the technologies which are used to image exoplanets, but also to kind of like give you an idea that if you have dreams, you can also fulfill them, and it's everything is possible, anything is possible. Anyways, so don't get scared away with these big words like adaptive optics. What is this? I'm just gonna give you a little idea about how you image exoplanets. So after, like at the end of this talk, you will at least get an idea, and you will be able to like explain in one line how you take the images of exoplanets. Also, if you don't understand everything, it's all right. Don't worry about it. Okay, just take it easy. Okay, so before I proceed further, I'll just quickly give you an overview about my journey. So I was born and brought up in Haridwar in India, and I did my bachelor's in information technology in Roorkee, which is not IIT, by the way. And I always wanted to do astronomy, but obviously, that was in 2004, so 16 years ago. And you guys know very well, you can understand how hard it is to basically explain to your parents, especially if you come from a very small town, what is astronomy, and how is it different than astrology. So I really didn't have any guidance, so to say. Except my mom just supporting me mentally. So I ended up doing my bachelor's in information technology. And then I decided, okay, I'm not gonna continue this field because I want to do astronomy. So I went to Paris to do my master's in astronomy and in astronomical and space-based system engineering. It was not core astronomy and astrophysics, but it was really more technical stuff because of my background. And as a part of my master's program, I got an amazing opportunity to fly to Hawaii to do my internship at Subaru Telescope. Then I came back to India, then I went back to France again and to Hawaii again to do my PhD, again in the continuing basically the the development of astronomical instrumentation for 8-meter large, 8-meter class telescopes. And after my PhD, before I move further, before this year 2004, I always wanted to be a part of NASA. Obviously, because Kalpana Chawla died in 2003, and I was in 11th standard, and I had a craze as well. Anyways, but at that time, I did not know the difference between astronomy and aeronautics. Note that, because I was more into astronomy. And she was obviously into aeronautics. She was an aeronautical engineer. So, but it didn't basically bother me. I just wanted to join NASA anyway, which I did actually after my PhD. I went to join Jet Propulsion Laboratory as NASA postdoc fellow, and I basically continued the development of instrumentation to find exoplanets. Then I came back to Paris as a Marie Curie Postdoc Fellow. Postdoc is what you do after your PhD. So postdoc is what you do. You're like an early career researcher. So it's like between like after your PhD and before your permanent positions. You know. So being a postdoc fellow is like you're on your own and you do your own research and you kind of like trying to make your own space in this vast world of astronomy. Anyway, so after finishing my postdoc in Paris, I now actually a few days ago I came to Canada and I'm in quarantine at the moment. So I'm gonna start my another postdoc, and I'm going to be working with TMT 30-meter telescope. Perhaps some of you may know about that, about this telescope. We'll talk about it a little bit during this talk. Anyways, so I basically okay. So just two more slides, and then we can hop on to what are exoplanets. So this slide is just to show you that I'm one of you, even though like, you know, I've been traveling quite a lot, just following my dreams, but it all started here in this small town, Jwalapur. And it's my parents. And I show this picture, my mom's gonna hate me, but I show this picture because I took the decisions of my life sitting on the scooter while my mom is washing things, basically. So the decisions of my life for the past 15 years. So it's really, one of you, and it's my brother, and here's my life is basically in these bags. I'm living on, you know, always traveling basically. So this is it's not an easy journey. It requires a lot of courage, and you need to have a passion for you know, for what you do. So it feels like sometimes that I'm just flying and not really able to settle down at a place. But well, that's the fun part of it. Anyways, moving on. So back in 2003, when I was 16 years old, this was my room. This was really my room. It's my brother. So obviously, I was really struck by a star, while a shooting star, I would say. Anyways, so I had a computer. I forgot that I named it Stephen because of Stephen Hawking, and I had this little ET here, and I made some, you know, stuff, spatial, blah blah blah, just because I was really I was crazy about everything related with space and astronomy. And this was my first window to the universe. This is really outside of when you go out of this room, you kind of see this, and that's where I used to observe 5 stars, basically. And then I had basically 2 turning points in my life. When I was in 11th standard, I had this physics teacher, S.K. Tyagi sir. He knew that I was I was crazy about astronomy, and I think he felt that I'm gonna fail my 11th and 12th standard physics exams because I was just into astronomy all the time. Anyways, he told me something which is actually still stays with me, and I'm kind of just forwarded to you. He said, well, actually, sorry, he asked me, what do you think, what is there anything that is faster than the speed of light? And I'm like, I don't know. I don't think so. He's like, well, close your eyes and go to Saturn. And I'm like, okay. So I closed my eyes, and I was just really circling around, you know, the planet Saturn. Then I opened my eyes, and he said, well, your thoughts are faster than the speed of light. So that was the turning point, one of the 2 turning points in my life, and I decided, wow, okay, my imagination is really faster than the speed of, even faster than the speed of light. So I'm just gonna do what I want to do. That's when I decided at that age. And then in 2005, okay, because when I was doing my bachelor's in information technology, most of my friends, they kind of made fun of me because I wanted to go to NASA. So at some point, I felt really disappointed because of the negative, you know, comments that I would receive in my college. So I ended up writing a letter, handwritten letter to NASA, and see this. I mentioned I was 17 and a half years old. It was such a stupid letter, but anyway. But they ended up replying back. they replied back to me. We can talk about this later on. I don't need to go into details, but they did reply back. See the date, 2005, and 10 years later, I joined them. So this was really these two moments were really turning points of my life, and I decided. I knew what I wanted to do. Anyways, so my journey. I really defined my journey as. Okay, this is bothering me. This little thing. Can't even move it. Okay, let's just move it here. So I kind of defined my journey so far with these heavy words. These may be heavy at the moment for you, but I've lived each and every one of these words, and that's what. Yeah. Anyways. It's not an easy journey. It requires a lot of, you meet a lot of, backlashes in your life and many negativity, and then you kind of have to like face everything by yourself. And so it requires a lot of courage. And if you're following a passion and if you have a vision, then you need to know that you're going to be, people are going to point fingers at you. So you want to endure everything, and you want to learn how to be resilient, Anyways, I think I don't want to scare you, but all right. Now, what are exoplanets? So these are the planets that orbit stars outside of our solar system. So stars other than our sun. So if you go to this website here, it will tell you, like, it's the screenshot I took from yesterday, and it will tell you like how many planets we have, how many confirmed exoplanets we know as of today or yesterday, and how many candidates are there. So candidates mean we don't know if they are planets or not. They might be, a lost planet wandering into space, or maybe they are like, companion, star companion. So we still need to confirm, at least 5,000 planets. And then we have like 3,000 planetary systems. So like just like our solar system, our planetary system, our sun and our sun with 8 planets. So currently we know at least 3,000 planetary systems in our Milky Way galaxy. So actually, okay, this height thingy bothering me again. I just want to show you this app. Perhaps you're already aware of it, but if you're not, then it's called this Eyes on Exoplanets. You can download it on your system. And what it does is like it's an interactive app which shows you how many planets we have discovered around us, basically. So you see all of these little dots? These are really the real, true planets we have discovered. And this is our sun here. So this is actually, they upgraded this app. You can actually go to a planet type and, you can basically choose, let's say, terrestrial exoplanets. So it kind of shows you how many of planets around the star can hold signs of life. Actually, I'm very careful about that. So let's go and maybe let's just click on the nearest one. It seems like this one is not. Well, we don't know which one is the nearest one. Let's just click on this star. And this basically, you can visit any star and you click on it, and then it will take you to that system, that planetary system. So you can see the star in the middle. It's moving too much. Star in the middle and a planet. So a planet name is basically the star name plus the character B. So it starts from B, not from A. So B, C, D, E. So that's how we basically name planets. So this is an exoplanet around the star, and you see this zone, green zone. This is basically the habitable zone. So if this planet was actually orbiting in this zone, it might have like a possibility to hold some kind of signatures of life. It's anyway, so you can play around with this app. Just wanted to quickly show you, introduce you to this app. Anyways, so the whole point of this talk is I'm just going to give you a brief idea about how we actually search for exoplanets, and I'm going to talk about one such technique where we actually take the direct images of exoplanet. It's like you take your DSLR camera and then you just point it to the sky and you just take a picture of it. It's not as easy as I say it, but well, okay. So, okay, why do we care about exoplanets? These are the questions that I ask myself. Like, I got my degrees. I don't need to continue. Nobody can take away my PhD degree, right? So, but why do I care? So it's not a matter of finishing my degrees, and that's why I wanna, continue this field. No, it's really the basic understanding, the basic, you have these fundamental questions, and that's what you want to join those human beings who are really trying to understand these fundamental questions. So, well, how do I say it? Is like, well, because we are curious, we are human beings, and we are curious, and that's why we want to find planets outside of our solar system. And you want to understand the formation, of how the planetary systems form and evolve around a star. It starts from star has like a circumstellar material around it, and it takes millions and millions of years for that material to actually turn into it's just a material of gas and dust. It takes millions of years to turn it into planets, and we don't really entirely understand. There are two. We don't really entirely understand how. We don't have a unified story that explains how planetary systems form and evolve. So it's still like we have two theories, but we still don't understand entirely. So we want to have more and more data, more and more data of exoplanetary systems, so that we can actually see a trend, to really see maybe there's the theory that can explain everything about how planetary systems form and evolve. And so, yeah, so the third point is really we want to see how similar such planetary systems are with our solar system. And we want to basically characterize those planets that can, that can harbor some kind of life. And we want to figure out if Earth is the only planet that holds life, or habitable planets are common. We just want to answer these basic questions, and that's why we care about exoplanets. Okay, so there are a few ways to search for an exoplanet, and they are classified in two different ways, two different techniques. One is indirect technique, and other is direct technique. So indirect techniques has few techniques in it, and direct technique is only one technique, which means take an image of an exoplanet, take a picture of it. All right. So before we move on to direct technique, let me just give you an idea about indirect techniques. Maybe you know already about it, but just it's like going through it, brushing up a little bit of concepts. So the indirect way of finding an exoplanet, you may figure it out just with the name, is that you don't see a planet, but you infer its existence around the star by studying the star itself. So one such technique is called radial velocity method, and this basically look for the wobble of the star. So basically, if you have a planet orbiting around a star, it's gonna the planet and star system are gonna orbit around their center of mass. So the star is obviously gonna wobble, and you can actually study this wobbly effect, and really see if there is a planet around the star or not. But you can also ask me a question that, well, this planet could be a star itself. Well, that's true, but I think, well, I'm not really well versed in this technique, but you have ways to know if it's actually an exoplanet, or if it's a star itself. So okay, let's say if it's a star that's orbiting around another star, then it's gonna produce heavy wobbliness, so to say, because of the star is heavier than the planet. So you basically look for the wobbly signal of the star to see if there is a planet around the star or not. So sometimes you don't have like success to really you get the data and you observe this Doppler shift for years and years to really to disentangle the signal. And so this was the first technique, actually, which this was the technique that discovered the first exoplanet around a main sequence star. So today we know at least 826 planets which are discovered by this technique. The next one is the transit method. So transit really means that if, it's like a Venus transit or, Mercury transit. You may have seen, like, you may have heard of Venus transit, when the Venus basically passes in front of the star, you can actually see that little black dot, for some time when it's transiting in front of the star itself, right? Our sun, sorry. So it's exactly the same thing, if you have, like, say, a few planets, a few exoplanets around your star, and if they basically pass in front of their star, what you're gonna do is actually, okay, so here we call it a light curve. So when there is no planet transiting in front of the star, what you see is like some luminosity. You measure some luminosity of the star, and then if there is an object passing in front of the star, you will see a drop in that luminosity. So that's a way to see, if there are planets around a star or not. And obviously, you need to do several observations in order to be sure that these are the planets, orbiting around the star. And if you can even, like, look at, like, this light curve here. If you have multiple exoplanets, your light curve will be a signature of multiple, it will see all of those signatures basically. So with this method, you can actually really see how far is an exoplanet, how many planets are there in the system, and how big they are basically. So this has been the most successful technique to find exoplanets. So you see, like, today we know at least 4,000 confirmed exoplanets, and out of those 4,000, 3,000, approximately 3,000 planets have been discovered by this technique. And you may have heard of Kepler Space Telescope. So Kepler has basically, used this technique to find all of these planets. All right, so I don't study those two techniques. What I study is direct imaging, so the direct method to find exoplanets. So this is one of the hardest. This is one of the difficult technique to find exoplanets. So here, what we do basically, you have a star. So a planet is really is such a a star is really bright. And for example, like when you go out during the daytime, you can't even look at the sun directly, right? And well, you shouldn't. And there are you can actually our planet, the system, the planets in our solar system, they are out there. We just don't see them because the sunlight is so bright during the daytime. But those planets are out there, we don't see them. So the same way, a star, you can't see an exoplanet just like that around a star. You need to first actually block the light of the star in order to see a faint signal around it. So it may seem very easy and straightforward. It's not. It's very difficult, but this is the concept. You block the light of the star, and then you find a signal of a planet around it, and you take an image of it. So, this technology is really This is technologically challenging technique, and that's why we have discovered only 51. Sorry, we have imaged only 51 exoplanets. So you may ask me, like, well, we know at least 4,000 exoplanets, and you're telling me that we have, you're telling us that we have taken images of only 51 of them. Really? Why not more than them? So this is what I'm going to talk about. This is extremely difficult to actually take images of these exoplanets, and I'm going to introduce you the technology which is involved in doing so. So there you go. Okay, so direct imaging. So all right. So yes. So it's very challenging to directly image an exoplanet, and we have imaged only 51 of them out of 4,000. And the reason I'm going to tell you why. Why is it so? So before I do that, actually forgot to tell you this. So this is like, all of these techniques kind of complement each other. There are people, different experts working on these different techniques. But I really like this one, not because I do this technique, but because it can, like, if you take an image of a system, it immediately reveals, how many planets are there. If you can actually, given that you can see those planets, you can like give, and this technique provides you a family portrait of a planetary system. You can actually see, and like seeing is kind of like believing. So it's exciting when you see an exoplanet in your processed images. You can also see planets in formation. So, we have beautiful images where we see like this circumstellar material around the star, and you have like a little tiny dot of, eating the little dot, which is like a proto planet, eating all the material, to become a planet itself. So you can actually see all of those things, and we have images, real images from big telescopes. And you can, in this technique, you can also see exomoons. It's very ambitious. It's so hard to see an exoplanet, and we are talking about exomoons. But yes, this technique can help you even see exomoons, which other techniques cannot. So it's very exciting, and that's why I'm in this field, and I'm still continuing developing, improving the technology. All right, so. Okay, remember I told you like you need to block the light of the star if you want to see anything faint around it. So it's exactly like when you have a solar eclipse. So when what happens during the solar eclipse, when the moon comes in front of the viewer and the sun, it blocks the light of the moon blocks the light of our sun, and you can actually see the prominences and solar flares. You won't be able to see this beautiful image of our sun if the moon is not there, right? So in some cases, in some really lucky cases, you can actually even see the planets of our solar system during the daytime, when during the solar eclipse, basically. So this is exactly what we're talking about. We need, is just our sun. When we look at a star, that's what we need to do. We need to block the light of the star so that we can actually see planets around it. That's exactly what we're doing. So, this is obviously a natural phenomenon, right? How do we do that in our telescope? We were looking at a star through our telescope. How do we actually block the light of a star inside our telescope? Well, we do that with an optical device called coronagraph. So it's just a piece of optics that we actually put at the focal plane of our telescope to block the light from the star. And it's extremely difficult, but that's what we do. All right. So what are the challenges? With this technology, like why we have imaged only 51 of exoplanets and not all 4,000 exoplanets that we know are out there, And actually, I forgot to tell you that the NASA statistic says that each star in our galaxy, in our Milky Way galaxy, has at least one planet around it. So what we are saying is that, there are billions of stars in our galaxy. So it means that there are billions of exoplanets out there. I forgot to tell you about that before. Anyways, so the first challenge is the light of the star is so bright that you can't see anything around it. Like even if you go out and look at a street lamp for like, let's say a few seconds, you'll feel already blinded by the starlight, right? So we can't really see anything. So there's a nice example here to show, like you have a lighthouse and let's say there's a little fly sitting somewhere on the lighthouse and you want to see it. And let's say this lighthouse is like several kilometers away and you want to see that. You want to image that beautiful firefly, let's say, sitting on this bright, light. What you need to do is basically, you need to turn off that light so that you can actually see the little signal from that little firefly. And when you know the location of the firefly, you can, study its characteristic. That's what we're trying to do, basically. So, it's extremely a planet is roughly a billion times fainter than the star, so it's extremely hard to see anything faint around a star, even if you block the light of the star, because there's another challenge that is there when we try to observe a planet star system from the ground-based telescope, so from the telescopes which are on the Earth. So, well, this is the first challenge, that your planet is so faint, is so teeny tiny faint, you don't even see it because the light of the star is so overwhelming. Yeah, okay, that's what I was saying. That yes. So for example, like if I tell you that, okay, you leave the planet Earth and you go at a distance of 10 parsec, you go 36 light years away from our solar system, and you look back, right? What you will see? Well, you know that we have our sun and we have our planets. You know that sun has, a planet Earth, which is 1 AU, 1 astronomical unit away from the sun, right? You know it's there, but would you be able to see it from 10 parsec away? No, you won't be able to just see the planet, because Earth is actually 10 to the power times 10 to the power 10 times fainter than the sun in visible light. So you can't really see that faint signal. And that's exactly what we are trying to do. We are now on planet Earth and we are just looking up to find planets, Earth-like planets, or just planets around a star which are really far, far away from us. So it's exactly like it's a reverse problem. So you can think it that way. Anyways, that's the first challenge. Second challenge is when we have like really big telescopes on the planet. A few what did I say? Yeah, we have ground-based telescopes, right? We have the biggest telescope we have is 10 meter. So the diameter of the telescope is 10 meters itself, right? So we use those telescopes to look up at the star. But looking up at the star through from the Earth is like looking down in a swimming pool, because we are looking through the Earth atmosphere, and the Earth atmosphere actually is very turbulent. It distorts the images of star. It's really an enemy for astronomers, the Earth atmosphere. So it's literally like, it's just a simple example, like when you see, a shadow of something, underneath the swimming pool, and water is turbulent. So what do you see? You see that, your image is not stable. It's not static. It's not static. Sorry, it's not stable. Static is not the good word. It's not stable, right? It's moving and it's distorted and it's like a blob of light. You can't really figure out what it is, right? It's exactly, it's a great challenge actually for us astronomers when we are trying to find planets with the telescopes on ground-based, on ground, basically. So the reason is because the Earth atmosphere, it creates, it's turbulent. We have like different layers, with different temperatures, and the air is kind of like get trapped in those different layers, and create kind of pockets of air pockets and stuff like that, to basically distort the light that enters the Earth atmosphere. So the light that actually leaves, that the light that comes from the astronomical object is basically traveling plane. It's all plane. By plane, I mean to say plane wavefronts. But then when the light meets the Earth atmosphere, it kind of like distorts the light. You can see like how it's just an animation showing you like when the light meets the Earth's atmosphere. It meets, the light is basically traveling through different mediums of different temperatures and different refractive index. And then what you see is basically, a big blob of light, and also the twinkling effect. So the twinkle, twinkle, little star poem is not good for us. That's basically, that's why stars twinkle when you observe these beautiful stars, from the, when you go and look up, star is twinkling. It's because of the Earth atmosphere. And we don't want the star to twinkle. We want to untwinkle the star, because we want the image of the star to be stable on our camera so that we can actually block that starlight. Just imagine if your star is just moving on your detector, on your camera. In our astronomical language, we called camera as our science detector. So I'm going to say detectors. What I'm trying to say is just a camera, okay? So the star, imagine if your star is really, moving around, and and it's just a big blob of light, because it's distorted by the turbulence created by the Earth's atmosphere. How are you going to block it? If your star is not stable on your detector, how are you going to block it, right? So what we need to do is, we need to untwinkle the star first. we need to make it stable on our camera so that we can block it inside our telescope. Okay, so these are the two main problems, with imaging, taking an image of an exoplanet. So I'm not really sure how much you guys know about telescope, but I'm going to give you a very quick idea. You don't need to understand everything. So how an image is actually formed in a telescope. In order for me to make you understand how you block an image of a star, I need to show you first how an image is formed in a telescope. So this is like a reticulating telescope. The light from the star is coming from your left side. Okay, these are the arrows. Follow the arrows, and then it gets reflected off the primary mirror, and then the light goes to a secondary mirror, and then it goes through the primary mirror where you have your camera. This is the Cassegrain focus where you put all of your instruments, a camera, basically to observe, to take an image of your system. All right. So the purpose of the telescope is really to collect, the light from an astronomical object. Okay. That's what I've been trying to say. Okay. And basically what you see when you take an image, when you point your telescope to a star, and when you look at a detector, on your detector, what you see is this. This is called the Airy Pattern. This is the image of the real image of a star that you see. And this is really the diffraction that happens, around the pupil of your telescope. It's really the ring pattern that you see in your camera is because of the diffraction. The light basically bends around the edge of the primary mirror. Okay, and so this is the image of the star that you see basically, and this is called point spread function. This is really the response of your telescope, of your system, to a star, right? So theoretically, let's say there is no turbulence, theoretically, if you have a telescope and you look at a star system, that's the image of a star that you should obtain. And this image is limited by the diffraction of the telescope. Diffraction by the telescope pupil. Okay, so this is also called in short PSF. This is simply the image of a star. That's all. This is just for us a technical term, and these are called wings of the PSF. And this is really, you can't avoid that because it's the diffraction pattern. It's a fundamental image that you can get, and this is the core of the PSF. So basically, this is the star image that you get, and the diameter, the angular diameter of the image that you see on your detector is determined by the diffraction of the light, and which is actually equal to lambda over d. So d is the diameter of the telescope, and lambda is the wavelength at which you're observing your system. Okay, so I'm going to talk about PSF. Okay, and PSF simply is the image coming out of a telescope, and I must tell you that this image really depends on the pupil, the telescope pupil that you have. So, for example, if you have a circular telescope pupil, you see simple airy pattern like this. You have most of the light from the star is centered at the core of the PSF, and then you kind of see the ring pattern. If you have a telescope, the primary mirror, which has a spider arms, so you may not know what am I talking about here. So let's go here first. So this is just like a simple small telescope. Okay, so this is your secondary mirror here, which is actually held by these spider arms, because imagine, like, you need your secondary mirror to reflect the light, right, towards your detector. How are you gonna hold your secondary mirror? You're not gonna hold it in the air. So what you do is, like, you add these little arms to actually hold the secondary mirror itself, right? So in your image, you will definitely see those arms as well, because this is the image you're seeing, right? So the PSF depends on the structure of your telescope, basically your primary mirror. So obviously, if you're going to add spider arms around, to hold your secondary mirror, you're going to add spider arms. You're going to see the diffraction around the spider arms itself, right? So if you change the location or the orientation of the spider arms, you will see the diffraction pattern moving as well, right? So this is what you, if your what I'm trying to say is that if your telescope pupil, let's say, looks like this should be the theoretical image of the star that you should get, okay? And this image is called diffraction limited, PSF. This is the theoretical image that you must get, you know, if you observe a star. But this isn't the case because we are observing a star through the Earth atmosphere. So what I'm trying to say is that if you have your telescope pupil, the spider arms like this is the theoretical PSF that you're gonna get. Okay? And so this is called the diffraction limited PSF. And just hold on to this concept at the moment, okay? Now, so what happens when the waves, the plane wavefronts that come from an astronomical object meets the Earth atmosphere? What happens? Basically, they, as I was saying, like, you know, they get into they encounter, you know, different air pockets of a different index of refraction, and what happens is like your plane waves are distorted, right? So normally, if you don't have an Earth atmosphere, you know, and you basically image, you take an image of a star, what you should see is a point source. It's like a simple point source. But what you see is a blob of light. So we don't really see a nice round image of a star, like a nice PSF. What we see, because of the Earth atmosphere, all the wavefronts are distorted, and what we see on our detector is it's just a big blob of light. Okay, and this is the problem for us because we want to block this starlight. Remember, we want to use a coronagraph to block the starlight, but we can't do that if it's just like a big, you know, just the light is so diffuse and it's just everywhere on your camera. So what we want to do is like we want to undo this Earth, we want to undo the process of what the Earth atmosphere is doing to our plane wavefronts, and that's actually okay. Before I move on in how we do that, first let me show you like a real example of how an image of a star looks like in reality. So remember I said we know that what is the diffraction limit of our telescope. We know how an image should look like from our telescope, right? We know the diffraction limited, but what we get is seeing limited. So seeing limited simply means that you're looking, you know, through the Earth atmosphere, and you're limited by what you can see. Really, it's simple. The layers of the Earth atmosphere where you have your telescope, you know, you're at a particular site and you're looking up, and you're at the mercy of the atmosphere, basically. So what you get is a seeing limited image. For example, like you're looking at these binary star system. When you don't have I'm not sure if these are real images. These may be simulated images as well. So if you don't have an Earth atmosphere, you must see two separate images of your binary star. But what you see is just a big blob of light, and you can't really see anything here, right? So this is what the Earth atmosphere does to your images. So instead of getting a diffraction limited PSF, remember point spread function, what we get is a seeing limited PSF. So instead of getting a nice diffraction limited PSF where you have most of your light concentrated at the core of the PSF, what you get is just a big blob of light. Okay, and in that case, the size of your image, the angular diameter, the angular size of your image is not lambda over d. D is the diameter of the telescope, but it's exactly lambda over r naught. I don't think so. I'm talking about r naught. Okay, forget about what I was talking about, because I'm not talking about the angular, the angular size of the seeing limited image. All you need to know is that we expect this, and what we get is this. That's it. And how do we basically go back to this? That's what I'm trying to say. So just to give you a summary, turbulence, created by the Earth atmosphere, that's what it does. It distorts the wavefront of your planetary, the signal coming from the star planet. It spreads the energy, received from a point source into a diffuse disk. Basically, this is a diffuse disk here. This is the point source, and it reduced the peak intensity. So this is the peak intensity is really at the core of the PSF. It reduces it, and it producing limited images. If you're getting this, how are you going to block this light? And this is just one image. If I show you a video of how this image moves, it's just like everywhere. So you can't actually block this starlight. So if you can't block the starlight, forget about finding a planet around it. Okay, it's a big problem. So what do? You use something called adaptive optics. It's a magical technique which undo all of these effects, and then it basically converges to a diffraction limited PSF. So you're not limited by seeing the seeing basically, but you adaptive optics undo the twinkling of the star, and it produces diffraction limited images, something that you theoretically expect. So how do you do that? So adaptive optics, I'm just going to show you this video. So this is a video by Gemini telescope, which is an 8-meter class telescope on the island of Hawaii. And how you basically undo the effect of the atmosphere. So before playing this video, let me tell you that in order to undo the effects of the atmosphere, first you need to study what your atmosphere is actually doing to your images at that particular state of time. So you basically study in real time the distortions, all the turbulence that is created by the Earth atmosphere. So for example, like here, you have this telescope on the mountain Mauna Kea in Hawaii, and it's looking up, right, at some star, right? So first, in order to undo the twinkling, what we want to do is first we want to study what the Earth atmosphere is doing to our images. So the way we do that is by shooting laser into the atmosphere. So let's turn the video. All right, so I'm just explaining you what is adaptive optics basically. Okay, so now what we are doing is basically we want to study how these four structures here. This is the spider arms, okay? And so the light actually is coming from top. This is your primary mirror. The light reflects to the secondary mirror, and then it goes through the primary mirror, which has a little hole, and this is where your adaptive optics instrument is, right? So you can imagine you're putting an instrument between your telescope and your camera, and this system, in this case, this green box is an adaptive optic system, which is gonna do the magic, untwinkle the star, and then will produce the diffraction limited PSF. Okay, let's see how it does that. And adaptive optics, just gonna explain you what is adaptive optics, AO in short. Okay, so you open the dome, and then what we're gonna do is shoot the laser up in the atmosphere, and we are shooting the laser up in the atmosphere because we want to study the effect of atmosphere. So what we're going to do is this laser will go at 90 kilometer in the Earth atmosphere to excite the sodium atoms, which has at 90 kilometer you have 10 kilometer layer of sodium atoms, and this laser is going to diffuse those atoms, and the light from the sodium atom is going to come back to the telescope. And that light which is coming back to the telescope, we study that light to really basically infer what the atmosphere is actually doing to your image. So this artificial star is called laser guide star, in short LGS. So LGS is really this is the island of Hawaii, and then you go on the telescope, Gemini telescope, the light goes back from the sodium atom, the light goes back to okay, let me pause here. Wait. Okay, so you see how the light was going primary mirror, go up, then the light is reflected to the secondary mirror, then it goes through the hole here, and then you have an AO system. And what an AO system does is in real time, it studies, how your plane wavefronts are affected by the Earth atmosphere, right? And how much they are affected, and then there are a few elements in the AO system that actually corrects those effects. So you have like some reflecting, mirrors and flat mirrors that reflects the light through your camera. Okay, so let me actually show you. I'll pause here just to show you. Here, okay. So this is an AO system, all right? So some of the light goes through a device. I'll tell you what it is later on. And some of the light goes through your camera here. So what you see here, you see, this is really how the image of your star looks like. Remember how I showed you the nice diffraction limited PSF, right? You don't get that. What you get is like big blob of, light moving in your detector. Can you really block that light? No, you can't. So what you need to do is like undo the effect of the Earth atmosphere. And how you do that is basically, I think it's going to show like these distorted wavefront that comes. And okay, so let me show you what's happening here. So your distorted wavefronts come, and you have seen like how your image is all blurred, right? So adaptive optic system, what it does is like it has two elements. One which is called wavefront sensor that senses how much your wavefront is distorted, and you have something called deformable mirror, DM, which actually undo those effects, right? So what's happening here? This is your DM, deformable mirror. You can say you can get by name that it's a mirror, a very thin sheet of mirror supported by actuators, and it's a mirror that you can reshape. So you actually reshape the mirror, in real time to undo, to basically make the distorted wavefronts plane. And so this is your wavefront sensor, which measures how much distortion is actually faced by each wavefront. So you will see like some of the light goes to the wavefront sensor. When wavefront sensor senses what's happening with your wavefront, it moves the deformable mirror to make the wavefront, the potato chips. That's what we call it, like these distorted wavefronts look like potato chips in such kind of animations, and then it basically flattens everything, and then you will see the magic. It'll give you back a stable diffraction limited image, or something closer to the diffraction limited image. The technology of adaptive optics, it's an art of shaping light. That's how I like to call it. So before I move on, let me actually just give you a very practical example of what is AO, like what really is an AO system. So it's like when you take a shower, right? You have like a hot knob and a cold knob, right? So you turn on both knobs, right? And then your body senses, it's a sensor. So your body is it's a sensor, okay? You get some hot water, and let's say it's too hot for you, and your mind will be like, oh, it's too hot. Let's just turn on the cold knob again, and then you will turn on the cold knob, okay? So your mind here is the controller. So your mind actually is controlling everything. When you sense something, it's really you sense something, and then you tell your mind, give signals to your hands to basically command if it should be more hot, if the water should be cold, or more hot or cold, whatever. Okay, so in this case, basically your body is a wavefront sensor, right? As I was saying, in adaptive optics, a wavefront sensor senses what are the distortions done by the atmosphere. So in our case, in the shower case, your body is it's a sensor, and your hands are basically deformable mirrors. So you're basically controlling. Your mind basically is a controller which tells your hands, okay, let's just put more hot water or more cold water. In the same way, adaptive optics, deformable wavefront sensor senses the distortion in the wavefront, and deformable mirror, it corrects it, okay? And we have a controller as well, control algorithms, which actually makes everything happen. So I hope it's clear. If it's not clear, then we can talk about it later on. Also, okay, so this actually is a real video that I'm going to show you, a video of a real star taken at Subaru telescope. So you have like, you're observing a star system, a star through 8-meter telescope. Subaru telescope has a primary diameter of 8 meters, and when we obtain images directly, with a telescope, we call them on-sky images. So images taken on sky. So this is a video, real video, when there's no AO, and you see like how distorted your image of the star is. And now, did you see the magic, by the way? I hope you didn't miss it. This is when we turn on the AO loop. It's when we turn on the AO system, and boom, we have like immediately we get the diffraction limited image. This technology is very sophisticated, not easy to do it, and if you have big telescopes, you need to have an AO system. And for example, like this technology is really barely starting in India. We have an institute called IUCA in Pune that has started to, work on robotics AO with Caltech, I guess. But we don't have from my understanding and from my knowledge at the moment, we don't have like an AO working at any of the telescopes in India. Okay, so but in the US and in France, it's really flourishing. This technology is also very old, and and they actually used this technology for defense back in 1960s. It was used for defense purposes by the Americans. So this technology is absolutely required if you are trying to use big telescopes to observe the night sky. Let me show you again this video. I really like it. This is your star is like really weird, and then all of a sudden, boom, you have a diffraction limited PSF. And now when you have a diffraction limited PSF, you can block this light, right? Okay, so before we move on, it's just to show you a simple, diagram so that you understand what's an AO system. It's just like the AO system is really, like if you look here, it's really built by three elements: deformable mirror, your wavefront sensor, and your control algorithm. Okay, so you have a distorted wavefront coming, wavefront sensor senses the distortion, and deformable mirror corrects it, and then you get the diffraction PSF. As results of AO. So this is, for example, so these are the Keck telescopes, the twin telescopes, one of the best telescopes on the planet. And they both of them have 10 meter, the diameter of the telescope is 10 meters, and they're on the island of Hawaii. They have one of the best AO system in the world. And the next time if you see big planet shooting a laser in the sky, you would know why they're doing that. It's because, they're trying to understand, they're trying to basically map the Earth atmosphere. So this is like a telescope image of Neptune. So can you imagine, like, you're spending millions and millions of dollars on creating this big telescope, and when you actually use it to image a planet in our solar system, and this is what you get. This is really disappointing, isn't it? Right? So you need an AO system in order to actually get an image that that you're looking for to really study all the details. And this is like another example, I think, is of Uranus. And this is with AO off, and this is AO on. Another example, I think this is by Gemini telescope, again on Mauna Kea, again shooting the laser to study the Earth atmosphere. And I think this is the image of the center of the galactic center, and that's where we have our famous black hole. And so this is the image when you don't have an AO system, and your AO system is off, and this is when your AO system is on. So you really see the stark difference, that AO system actually gives you. An AO system is must. Anyways, okay, all right. What is it now? Okay, so okay. So this is just a simulation which I did. So for example, like if you have a telescope pupil, all right, okay. So once you do the correction by adaptive optics, once you stabilize your starlight, now you can block it, okay? But that blocking is also not easy. So the first problem is solved. The Earth atmosphere is solved by the AO system. Second problem, your star is super bright, and how do you block it, right? I'm not going to go in details, too many details, and I think we are at the end of the talk. Hope you're not too sleepy. Anyway, so I'll just tell you very quickly, like when you have a circular, let's say you have like a circular pupil of your telescope, it's just a simulation. You do the Fourier transformation of this telescope pupil, and what you get is theoretical PSI. you change the structure of this pupil. For example, you look at this pupil. This is how the telescope, the pupil of the TMT telescope would look like. So TMT is a 30-meter telescope, which is built by 5 countries: India, Japan, China, US, and Canada. And when you take the Fourier transformation of this telescope, this is the theoretical diffraction limited PSF. So you see, like, this is all unwanted. This is really the diffraction pattern, and we can't avoid that, right? So when you block this starlight, you only block the core of the PSF. You can't block this like unwanted residuals because of the diffraction pattern, and that also affects, that basically kind of explain that we can't really block the starlight entirely, and that's why we don't really see exoplanets, because it's so hard to see anything lying underneath those, even those rings and this diffraction pattern, because these are still very bright. Then it's bright. They are brighter than the image of the faint image of the faint signal of your planet. Anyways, so first you have the diffraction, which is a problem. Second, which is unavoidable, and second, if you really look at this PSF through the Earth atmosphere, again, that's what you get. Like, as I was saying earlier. So let's just see. Okay, that's what I was saying. Like, let me just stop here. Here, okay. So this is just a simulation. What I did is, like, in this simulation, I have a coronagraph at the center, which should block the light of the star. Okay, so I'm just showing you, like, if you you just move the star out of the coronagraph and then well, what I'm showing you is really this is when you have a little coronagraph here. When your star is actually stabilized behind the coronagraph, you see nothing. This is theoretical, but this is not the case in reality, right? That's what you want the star to be completely blocked. And in this case, I didn't simulate any planet. If I simulated any planet, it would have been, visible here. But that's not what happens in reality. So, for example, like, this is the PSF of the TMT pupil, and you will see that you have. Let me just block here. Stop here. Okay, this. So this is like after you. And this is a case when there is no atmosphere, okay, and you simply looking at a star through the TMT pupil, and you basically block the light of the star. Your light of the star is not completely blocked because of the diffraction pattern. Like, you see, it's when you don't have a coronagraph, that's what you see theoretically with no atmosphere. But when you have a coronagraph, you still see some light, even though there is no atmosphere. So this is something we cannot get rid of. This is a diffraction, right? And that is why we actually, even though after blocking the starlight, we still don't see planets, because they are actually hiding underneath these, the residual by diffraction pattern. And this get worse when you actually add the Earth atmosphere. Anyways, okay, we're approaching the end soon, 2-3 slides more. Okay, so I hope I gave you an idea why it's so hard to actually take an image of an exoplanet. So let me actually show you how an exoplanet imaging instrument looks like. Whatever I told you, in simple, I try to tell you everything in simple language. That simple thing is actually done by these beasts. So this is the instrument where I did my PhD, and the instrument that are used to do the AO, use the AO to undo the effects of twinkling the star, to undo the twinkling effect, and use a coronagraph to block the starlight. This collective, the instrument is actually the instrument which has these two techniques. They are called extreme AO system, XAO. Basically, it's just a fancy name. This is an extreme AO system. It's called SKEX-AO. It's a Japanese-French system at Subaru telescope. So this is a Subaru telescope in Hawaii. These are the Keck telescopes I was saying before. But this is really, it requires a lot of many optical elements to do so, basically. And so these are the bottom and top system here, when you open them, that's how they look like. They're the beast instrument. Anyways, so this is so we have basically mainly 3 instruments on the planet, which are making efforts to find exoplanets. So one of them is this called SkexAO instrument. That's where I did my PhD. And we have another one. Yeah, okay, before that, actually, I want to show you this video. It's pretty cool because this is a real extrasolar system. But remember how I was telling you that I really like this technique because you can actually see with your own eyes, exoplanets orbiting the whole family, whole portrait, a family portrait of exoplanets around a star. So this system is very famous. It's called HR 8799 in the middle, and you would see that it's blocked. You won't see a star because it's blocked in our instrument. And let me tell you, actually, when you observing a star and you close your AO loop and you have like your starlight is stabilized and you put a chronograph and you block the starlight, and in your live images you see blocked starlight. But let me tell you what, in those live images where your star is stabilized and blocked, still you don't see exoplanets because you still have, if you may remember, you still have residual starlight because of the diffraction pattern, which get worse because of the atmosphere, because the correction by AO is not perfect. Nothing is perfect anyway. So you need to do post-processing. So you take your data and then you process them later on with smart and intelligent algorithms to basically get rid of the diffraction, the residual light, basically. And then once you do the post-processing, then these beautiful images of your real planet emerges. You don't see exoplanet images in your exoplanet signal in your live images until the exoplanet is really, really bright. Okay, so this is not an animation, it's a real system. It's a real system, and you will see like this is the data taken, I think, over 80 years at the Keck telescope, and what you see is 4 planets moving around the star, and they kind of like we need to have more observations in order to actually see a full orbit. I mean, decades of observation in order to see a full orbit. And I think this is just a slow motion video, but these are really four real exoplanets that you see orbiting the star. So this is pretty cool about direct imaging of exoplanets, and that's what we want to do with the with all the planets that we have discovered. We know they're out there, but we still can't image them. And you see the reason. Okay, you will see, like, you see this thing, like, forget about the planet, but you see like these evolving structures around the star. This is because of the atmosphere, because we can't, AO is not perfect, and we can't really do much better than this. Really, this is a very famous system in our field, and I must tell you, you can ask me, well, why don't you go to space? Yes, we can go to space, and we are going to go to space, but we won't need AO system, sure, but we are still affected by the vibrations of the telescope, and the vibration of the telescope will create, will destabilize your starlight, will also affect the images of your star. Okay, and it will produce such effects. Like, this is all residual starlight because of the Earth atmosphere. Oh, sorry, in this case, because of the Earth atmosphere. But in space, when you're in space, you're observing, a star system. You're pointing to a star, and obviously you're gonna track the star. How are you gonna track the star with a telescope? You're gonna make the telescope motors run, right? The reaction wheel of the telescopes are gonna run in order to keep tracking the star, and those reaction wheels are gonna create vibration in your instrument, and those vibrations are gonna do something similar to what the Earth atmosphere does. So it's extremely hard to even image exoplanets from space. And you see, I think these planets are very far away. These are, I don't remember exactly, but I think the nearest planet, I may be wrong, we need to double check. The nearest planet that we see in the system is roughly 40 AU. We need to double check this number. And you see our Jupiter is 5 AU away from the star. So there may be more planets here. We don't know that, we can't really, we have no way to image them because we need to block all of this evolution of the starlight in order to actually see these faint signals. Okay, so anyways, okay, let's move. So this is this video has been taken by Gemini, not the Keck telescope, sorry. Yes. So as I said, we have 3 instruments of the planet which are making efforts to find to image exoplanets. The second one is not, I say second not because it's second in number, it's just that I'm saying the other one is Gemini Planet Imager, GPI in short. It's one of the most famous, well, we have only 3 systems, and it's an exoplanet imaging machine, very active, and GPI is an effort by Americans, mostly by Americans, and this is now, well, GPI was at Gemini Observatory in Chile, and now it's moving to Hawaii. This instrument, not the telescope, just the instrument, is now moving to Gemini North. And it was in Gemini South, Gemini telescope in Chile, so Gemini South, and Gemini telescope in Hawaii, so Gemini North. Anyways, so these are like some beautiful images of real exoplanets, around stars. So just some results that you can see. At the middle, you have the starlight is blocked, and then all these little specks of light that you see is really the, residuals of starlight because of the Earth atmosphere. And for example, like this is not a planet, it's a brown dwarf. Okay, so you have like, well, these are the beautiful, this is a video that we saw, HR8799, so CDE, we don't see the planet B in this particular image. All right, and another system is called SPHERE. SPHERE is a European effort. So this is the SPHERE instrument. Again, this is at the VLT, Very Large Telescope. And this is, with the GPI, I'm showing you like the images of real exoplanets. With SPHERE, I'm showing you the circumstellar material around the star. And these are beautiful images, like these are real images. You have the star in the middle, and what you see around it is the circumstellar material where the planets might be forming. For example, in this case, you see this little gap here, and the little gap here too. When we have like gaps like this, and we have rings around the star, it means that the planets are in formation. There might be a planet that actually swept out all of these like this material around the star. So there might be, like, as I was saying, you see the planet in formation. So direct imaging is really an awesome technique. Anyway, so these are the 3 instruments. In future, if you would like to work for these instruments, I'm just telling you their names. SPHERE instrument in Europe, European efforts, and GPI, it's moving to Hawaii now, and Skexeo is a wonderful instrument where it's pretty open, and you can do your PhD in this instrument basically. Okay, all right. So just to summarize quickly, so this is a question we started with: why out of 4,000 exoplanets we have imaged only 51 of them, right? Well, Earth atmosphere is a big problem, right? We need bigger telescope. That's something we didn't talk about as of now, but we need 10-meter telescope is not enough. We need bigger, and that's why we are making efforts to have much bigger telescopes on the planet. So TMT, it's going to be like an international observatory, and India is a part of it. And on the other hand, Europeans are going to make ELT, so extremely large telescope. They're going to have, I think, the primary diameter of their telescope is going to be 39 meters. So it's going to be even bigger than TMT. So we need bigger telescopes. If you want to look closer into a star, you need higher resolution, and you're going to get higher resolution by having bigger telescopes. Okay, so 10-meter class, not enough for us. And also because, with the current technology, the adaptive optics and the way of blocking the starlight, with these sophisticated technologies, we can find only those planets which are 10 to the power 5 times fainter than their star in infrared light, not even invisible. Any planet which is much more fainter than this number in infrared, we can't see it. We cannot see it. So basically, these are mostly gas giants planets that are much brighter planet, and they are roughly 10 to the power 5 times fainter than their star, and that's why we have actually imaged mostly gas giants, right? Because this is because we are limited by our technology, and we need to improve it so that we can see much fainter planets, and we can see only those planets that can also emit their own lights, which are like self-luminous. We can't if we can't really see we cannot image a terrestrial exoplanet from Earth. Forget about it; it's not happening because we don't have the technology. We don't have the eyes to actually see terrestrial planets because they are very faint gas giant planets which can emit their own light as well, because we can see them clearly. So with the current technology, we cannot image Earth-like planet around a sun-like star. We need to go in space, but then in space we have problems as well. As I said, we need bigger telescopes to be able to see a star closer, a planet closer to its star. But in space, on the Earth we can make big telescopes. We are building 39 meters now, but in space we can't send big telescopes. The biggest telescope that we can send is 4-meter class telescope. 4-meter monolithic mirror. Monolithic mirror means one piece of mirror itself. And so we can, with the current launching technology, we can send only a monolithic mirror of 4 meters. We can't do more than that. What we need to do is have the segmented mirrors so that it can be folded and then unfolded in space. But then in that case, VR technology, there's a problem as well, because when you actually use different segments of mirrors, you want to phase them. You want to do co-phasing of all of these mirrors in order to actually get nice images, the diffraction limited image of a star. And this is a huge problem as well. People are studying, trying to improve the technology, how we can co-phase. We can send big telescope in space, but it's going to be in pieces. But how are you going to align those pieces? If you don't align those pieces, you're going to be affected by the diffraction, the residual starlight, and you're going to spend millions of dollars, but then won't be able to image what you wanted to image, terrestrial like exoplanets. This is really a challenge. All right, so quick thing. So from the Earth, I think I already touched upon this point, but on the Earth we have these two class telescopes. On the northern hemisphere, we have the island of Hawaii, where we have I think 13 telescopes. I think maybe 11 of them are working. So Keck telescope, Subaru telescope. And then in the southern hemisphere, we have VLT, very large telescope, which are actually used to find planets. And so the current big telescope, the size is only between 8 to 10 meters. And we can image only giant planets which are lying very far away from their star. The further apart they are from their star, the more easier for us to see them. And in future, we're gonna have these big telescopes, as I said already, ELT, TMT. This is gonna be Giant Magellan GMT telescope. It's gonna be in Chile. This is gonna be in Chile as well. And this is, we don't know, probably in Hawaii. So with these telescopes, we will be able to image terrestrial planet, not Earth-like planet, but just cooler planets at less than 5 AU, so at the scale of our solar system. Let me just skip the slide because I just thought it was cool. Why it was cool? Because where's Subaru telescope? Subaru. Okay, here. So you have Subaru telescope, 8 meters. You have Keck telescope, 10 meters, and look how big TMT and ELT are going to look like. This is a primary mirror of your telescope. It's pretty exciting, actually. Okay, we touched upon this, the problems from space. We sure do not need AO system, but the wavefront is still going to be distorted because of the misalignment problem, because of the vibrations and stuff like that. And so we do need a coronagraph to block the starlight and then to correct the wavefront distorted by the misalignments and the vibration issues. And as I said already, we can't launch, or not launching technology is limited, and we can't launch more than, I think, 4 to 6 meter class monolithic telescope. Again, monolithic is one big piece of mirror. And well, JWST is gonna be, is gonna come in near future. It's gonna be 6.5 meters, and it's gonna be pretty exciting to see this telescope. Another one is gonna be Roman Space Telescope, and these telescopes are kind of like a technology demonstrator. We can send stuff in space, but we need to. We have Hubble Space Telescope in space, and it was not designed to image exoplanets, even though there is a chronograph in that telescope, but it's really, really old technology. So we're really relying on JWST and Roman Space Telescope, and this demonstration takes time and a lot of efforts, basically. And we have actually more telescopes concept being studied, especially at NASA, the LUVOIR and HEVEX system and Starshade. I think maybe you've heard of Starshade. We can talk about them later if you have questions. Anyway, so second last slide. Okay, so what's next for me? So I'm here in Canada. I'm gonna start my job in a month, and so I'm gonna be actually working on the prototype of a direct imaging instrument for TMT. So I'm very excited about that. So I'm gonna do a lot of simulations and a lot of testing in the lab to basically give this concept. The concept is already there, but work on this concept and then see what can we actually do, what we would be able to do with such an exoplanet imaging instrument for TMT class telescopes. And that's it. Actually, I have some advice for you, because maybe like some of you are not really in this field at all, maybe don't really care about what I'm talking about, but whatever you want to do in your life, whichever path you want to take, maybe you want to be a fashion designer, who cares? This is something that I want to share with you, just a few points that actually helped me to be here where I am today. Really listen to your inner voice, because your inner voice is there to constantly guide you. It's always guiding you, so always listen to it. And I say that even more because I know where we are coming from the Indian culture. It's really difficult for us to follow our dreams, because we have so many other family responsibilities and social pressure. If you can really just like set everything aside and listen to your voice, it's gonna really guide you. Trust me on that. And be an observer. I've always observed things around me and be a patient listener. It's very important that you listen to things around you and observe and don't judge. And always treasure your dignity and self-respect. And I say that because the moment you move on in your life, you will encounter many problems, many difficulties, people pointing at you and you not knowing what to do. In those moments, if you know what you're trying to do, and if you know you're right, just hold on to your dignity and self-respect. Maybe like a talk given by a guru, but doesn't matter. I just want to share this with you. Be really firm about your ideas and dreams. And I say that because I know what it feels like when you clash with your parents, that you want to do something and your parents have no idea. And your teachers, your classmates have no idea what you're talking about, because they know what the society has done so far and you're trying to do something different, right? So don't get polluted by what people don't get polluted by what others have to say. Be firm about your ideas, but be polite about it. Don't be don't have a wrong attitude. Basically, be polite and humble about your own ideas and your dreams. And don't be afraid to make mistakes. I've done a lot of mistakes in my life. I've done a lot of mistakes. Thankfully, not grave mistakes, but I did mistake. I did. I'm a human being. Don't be afraid to make mistakes. People will judge you. Just don't care. Really, it doesn't matter. Make mistakes and take a lot of risk. The journey that I shared with you, my journey and the things that I'm showing about these technologies, I took a lot of risk in my life. And, I also go through imposter syndrome. Maybe some of you know about it. Imposter syndrome means that you don't believe in yourself, and you think that people are gonna figure out that you are an imposter, that you're not real, that you are pretending. That's an imposter syndrome, and most of us go through it, right? So I even go through that. Okay, so it's not that everything looks flashy and everything is perfect in my life. No. So anyway, you take risk. You don't fear the unknown. You don't fear anything. You don't know what's out there, so why fear about it? Why don't you just go and explore what's out there, right? Why think? Why look at it? Why can't you just see? Okay, what's out there? Let me find it out myself. Why should I look at what other people say? Oh, don't go there. It's bad. No, let me find out myself. I'm gonna go and find out myself. Anyway, just jump and dive. Whatever you're trying to do in your life, just do it. Really, don't worry about my father's not going to support me, my parents want me to get married, and blah, blah, blah. Just put everything aside politely, not disrespectfully, politely, because we need to respect our culture, our cultural values, our parents, right? That's your journey. You will have to figure out how to do it, but just jump and dive deep, really. Alrighty, and these other references that I thought might be useful for some of you, I can share this whole slides, actually, everything, presentation, with all of you, not a problem, and you can go through these links. And some of the fun reading that I always recommend to the students, especially the last one, which really talks about how NASA actually started in the US, how they actually sent the first rocket. I think it was Explorer to the into the space. It's very nice. This book is amazing, by the way. Anyways, I'm done, and I'm sorry I took a lot of time, and you must be sleepy. I'm sure some of you must be yawning. But anyways, I'm happy to take questions.
Yeah, so there are quite a bit of questions waiting for us to get back to.
Okay.
I don't think we can answer all of those, but then maybe we can have a Q&A session on Instagram, or maybe a podcast on these questions, if you would like.
I'm not on Instagram. I'm such a oldies. I'm not on any social media.
So maybe we can have a podcast. We'll figure that out later. For now, let's take up questions. Okay, so right now,
I'm just gonna say that I just want to say two things. First thing, I'm okay with time as long as you guys are. Second, you can also send your questions to me by email. I think I shared the email. This is my email address. You guys can send me questions here as well. Okay, go ahead now.
Yeah. So in this meeting, we have questions as such. Dhanush Salunke is asking, how do astronomers measure the temperature of faraway planets?
Temperature of faraway planets. Well, wow, that's such a nice question. How do we measure the temperature of exoplanets? Well, actually, when we look at the transit techniques. Oh, this is such a good question. Can I get back to you on this question? Maybe whoever asked this question, can they send it to me by email? Because I don't want to say something stupid, because I do more technology, not the theoretical aspect of what do you do with the exoplanets. For me, my job is I give you the exoplanet, you do whatever you want to do with it. Anyways, can you please, whoever asked this question,
to you on email. So let us just move on with next question. So Priyal Bodia is asking, isn't this telescope technique similar to the one they are using at Caltech, the one they use to detect the black hole in center of Milky Way?
Yeah. What's the question again? Sorry, the one that.
So she's asking, is this telescope technique very similar to the one which was used in Caltech for detecting the black hole in the center of the Milky Way?
So if I understand, I think if I remember correctly, they do use AO systems, obviously, because we wanna have because we are observing the big center. So yes, AO was used. So AO does not have only one application. AO has many applications. So I was just talking about in the context of exoplanets. So we use AO for for most of the astronomical observations. Yes.
Okay. So next question is again from Dhanush Salunke. He's asking, do any exoplanets have rings?
So the question is if the exoplanets have ring.
Yeah.
Yeah, they must have rings, but we haven't seen them because it's anyway so hard to see the exoplanet, any exoplanet itself. But yes, they must have rings and exomoons, and but we don't have a proof yet because we haven't seen one yet. But they must be, yes. Saying like the name of the exoplanet is given after its star. So if the star name is 581G, the planet would be the first planet, the nearest planet that would be to that star would be 581GB, small b. That's it.
Okay.
And then we just give like C, D, E. So we kind of just like give them the small b, C, D. In exoplanets, we were like, okay, can we actually use HST, Hubble Space Telescope, to confirm the planets that have been discovered, we are discovering. So HST has been used to reconfirm the planets that we are discovering, but it was not designed to find exoplanets. So it doesn't have a technology to actually look for, rocky exoplanets or super Earths or terrestrial exoplanets. We can't use it just for that purpose. We mostly use it for reconfirming. And actually, people have actually gone back. There have been like data which was archived many years ago, and people have gone back and they dig down those data, and those planets were actually there. It was, we just didn't see them before. So people have reprocessed those data. So and then JWST and RST, Roman Space Telescope, is gonna go in space. Yes. So we are mostly relying on Earth-based telescope basically to find image planets.
Actually, Sairaj is asking for an advice. He's saying,
Okay.
I did my bachelor's in PCE and would like to transition to aeronautical engineering or space systems engineering as master's. And also,
Okay.
I would like to pursue my career in space industry. So, what are the opportunities after the master's in USA, Europe, and elsewhere?
Oh, that's such a long question, and it would require some time to explain. Basically, I'm actually looking at the question. You did your bachelor's, okay, and you want to make a transition to astronautical engineering. I see. So, well, opportunities are ample in US and Europe if you want to just find,
Maybe
program.
you can just mail you and you can get back to him.
We can do that as well. Yes.
The question isn't that clear.
Yeah. Yeah.
Okay, one question is that Parab is asking, how exactly does the deforming mirror deform? So, I
How
guess you
does
gave example of shower. Deforming mirror deform.
Well, it's a very thin piece of thin layer of mirror, and it's supported by actuators. So actuators are basically the little units that kind of like move up and down to basically deform this mirror, and it exists and it can do it. It's you just command basically, you just send commands to the actuators, and the obviously the more actuators you have, the more degree of freedom you would have to move the surface of the mirror, and the more you can provide more correction by more degrees of freedom. So just a thin piece of glass supported by actuators, really.
Does anyone else have any questions? So let us wait for 1 minute.
I mean, if people want to have questions directly, they can ask me directly as well instead of writing.
Yeah.
Well, I have one question. Okay,
Sure.
so as per I know, NASA releases data regarding exoplanets every year or every intervals. So, as a part of citizen scientists, how can we actually use that data to find those exoplanets? I mean, how do we recognize those planets in that data? Because they might be into like numerical forms, right?
Yeah. So actually, there are several efforts where you can take part in Data Challenge. Have you heard of Data Challenge by NASA and by other groups as well? So Data Challenge is basically it's open to anyone who want to join, and they kind of like give you a training on. They give you the data and they give you training what actually you can do what techniques you can use to search for a possible signal from a planet in that data. So it's a data challenge. There have been actually several data challenges where anybody can participate and then attend those 1 day long lecture or something like that, and then have, you would be part of a team, and then you can work for a month and then come back and then basically I don't know the results, but I think you can be a part of that. I think it's let me see from data challenge. Data challenge. Let me just find a website so that I can share that with you. I may have mixed it up though. Or you're trying to, or you were asking like, how do you yourself figure out if it's what you see is a signal or not?
Yeah, myself. I mean, kind of a project if I have to build.
Able to do you can, but you won't be able to actually do everything by yourself, obviously, because you would need to connect with somebody who can help you, explain you the techniques, because the data is available, but we use very sophisticated post-processing algorithms. So you would need to actually first understand those algorithms in order to apply those algorithms in your images. And then if you have a data, if you have an exoplanet signal, it would emerge out of it, right? So, and then obviously, if you see a signal, you don't know if it's a planet or if it's a background star or if it's a brown dwarf. Obviously, then you would have to connect with people who provided that data in order to go through other processes, to really see what you produced is actually, a stray data, or it's actually something, real, or it's not a false positive. Yeah. I actually shared something. It's an exoplanet imaging challenge. Maybe like, you would need to be a part of a few groups to be able to understand how you can actually differentiate between false positives and the real signal.
Yeah, that will help.
Okay.
That's all for today, I guess, ma'am.
Okay. Well, I'm glad. Well, I hope I didn't provide too many technical details, or I hope it was okay to talk.
Yeah, it was. I received a very good feedback in between. It was helpful because
Okay.
instrumentation isn't that developed in India, right? So people are finding this insightful, I guess. Thank you so
Okay,
much.
that's great.
Yeah,
So I shared this.
sorry, ma'am, I couldn't hear.
How much researchers? There's a question, I think. How much researchers in your field get paid? Is that an Indian question though? Anyways, it depends. It really depends, because when you, as a PhD student, you are really poor. I mean, obviously, you get more in terms of doing a PhD in India. In India, I think you get, I don't know how many thousands of rupees, but in US, or in the US, I used to get $2,000, but then I would pay $500 for taxes, so $1,500 as a PhD student. But then it's actually not enough when you're living in Hawaii. And I think in France, you get, I don't know, 1,700 euros before taxes, or maybe less than that. I don't really know. So as a PhD student, you don't get enough. But then later on, when you join as a postdoc fellow, then it depends if you are hired by someone or if you actually obtain a fellowship. Because obtaining a fellowship is prestigious, because you bring your own money. You bring your own money to do your research, to get paid, and you just like it's more like independent sort of. But when you are actually, and in those cases you are paid more, basically. I mean, so it depends, like I don't know, like when you're working at if you have a NASA postdoctoral fellow, then you're paid like $5,000 US dollars before taxes, but then you pay a lot of taxes, that state tax and federal tax. So in hand you would get, I don't know, $3,500 maybe. And it depends, it's different in Europe, obviously. But then if you're hired by a research institute, then your pay would be $4,000 before taxes. So I would say that in hand after taxes, you would get maybe between 2,500 to 3,000 Canadian, not Canadian, US dollars, I think. Well, and I'm not really the best person to ask anyway, because I'm not. I pay a lot of taxes. I think a bit more than the Americans. I was paying, not now. Now I don't know how much I'm going to pay. Anyway, I hope that answered your question.
Yeah, that that should be sufficient, I guess. Yeah, so we are about to end. There are only 5 minutes left to end this meet. And
Okay.
we are honored to have you, ma'am. The efforts you took, and overall, just a big thank you. Very big thank you. And we hope to see you soon again.
Sure, you're welcome. It was my pleasure. It was really my pleasure. Okay. And sorry to everybody who just wanted to go to bed and I kept them awake, telling them AO and chronography. And anyway, so all the best to everyone and have good luck with whatever you're trying to do. And send me questions if you have, later on, if you can send me questions. And good luck with everything.
Ma'am, have a wonderful day ahead. Bonjour.
Thank you. I left France behind, so I'm back to the English speaking country. So
Okay.
I will say au revoir, not bonjour. Au revoir is for goodbye.
Yeah, I said bonjour. Like, have a
Au
good
revoir.
day.
Yeah,
Au
okay.
revoir is goodbye. Yeah, I know. Okay, so au
Okay,
revoir.
cool.
I'm
All right,
pronouncing it.
all the best, everybody, and take care. Bye.